Okay. Good morning or good evening, everyone. Welcome to the second session of our webinar series created to the collaboration between SmartFluidPower and VIS Hydraulics. And if this is your first time joining our session, let me briefly introduce myself. I'm Simone Serafini and I handle marketing and communication for VIS Hydraulics and SmartFluidPower. In this series, we'll show hands-on how dynamic simulation applied to industrial use cases can support every phase of the design and optimization of hydraulics components or systems, helping you develop faster and reduce issues at the bench test. In the previous session, we saw how to build a parameterized hydraulic valve model in real time and validate its functionality, behavior, and performance. If you missed it, I shared the link to the technical deep dive in the chat. And today we'll take it one step further. We'll move from a single component to a complete hydraulic system all the way to its validation. Marco Rizzoli, one of SmartFluidPower administrators, will guide us through the entire process. As always, the Q&A section or the chat is available for any questions, and time permitting, we'll address them toward the end. Marco, over to you, and enjoy all the session.
Thank you, Simone. Welcome all. Okay. The topic for today's meeting is the simulation of the system and of the entire system. At the end, we will add a detailed valve to see how they can be connected and see how is the overall behavior of the system with a detailed valve, the valve that has been studied in the previous meeting. I will spend just a few minutes to introduce SmartFluidPower if someone missed the first meeting. And then we quickly move to the main chapter of today. Since we have not a lot of time, so I will be very short with the introduction. SmartFluidPower is okay. We are a small SME that was founded in 2018. We born from a University of Modena and Reggio Emilia, and actually we are independent and we are in the industrial field, still promoting simulation and proposing this type of tool to simulate and predict the behavior of hydraulic component and system. And we have as a partner, we have a member from the academic field, but also from the industrial team. Our solution is based on virtual models, since it means that we are able with our computer to predict the behavior of the component. This helps us to reduce the number of the prototypes and of tests that we normally perform on the test rig or the test bench. And with the simulation also it is possible to expand the system or the layout for the testing. I mean, how often it happens that if you are a valve producer or a component producer for the for the fluid power field, how many times do you design your model, you test it, and then when you deliver your product to your client, you receive a feedback with different response, different behavior, and with simulation we try to anticipate this feedback. So it is possible for the designer to have a relation one-to-one, a ratio one-to-one from the modification you have in your design to the response of the model, the virtual model. This helps to reduce the costs, but also to have a faster time to market. Our solution is based on Modelica language that is a multi-domain system and helping us to simulate both the fluid power field with interfacing with the kinematics of the mechanical library and the electrical library. And so we have the possibility to command the hydraulic system and see what is the response to the output, to the mechanical output. It is based on the open source platform that is Open Modelica, and this helps us to focus on the hydraulic library that is our main product, and we are all trained to develop this type of elements, while the platform development is given to the Open Modelica team. This separate the roles and help us to focus only in the fluid power field and to reduce and keep low also the cost for this type of solution if we want to compare to other existing possibilities in this type of simulation that is a lumped parameter simulation. It is based on drag and drop block build, so you can build your layout with the drag and drop system. And there is also code, but with our library, you don't need to learn how to code. It is enough to understand the logic and the rule we use for the connection between the blocks. The library has a structure and it is divided in sections. The first one is the hydraulic section, is the more generic one that contains valving, pipes, orifices, and pumps. And then we have the mechanical library that help us to interface the hydraulic library with actuators and with motors. We have then a very important live package that is the component package that allow us to design in detail the valving, the valve mainly. And then some extra that are signal and accessory that we use to control and command the other library, the hydraulic libraries. So, to conclude, we mainly develop this simulation tool, but we do also consultancy for our clients. We offer training in fluid power field, but also in simulation, and we support the companies in their R&D projects. Okay, we can move to our today's example, that is the simulation of this type of circuit that describe a system with a regenerative system. Starting from the power unit, here we have a fixed displacement pump controlled by a relief valve that discharges the extra flow rate. After the relief and the pump, we have distributor that control the direction of the pressure that we generate, and a double acting cylinder at the user, at the end of the circuit. This double acting cylinder is equipped with a regenerative valve that allow us to multiply, to increase this exiting velocity of the cylinder with an electrical connection, so with a command, electrical command. There is no hydraulic piloting. There is the possibility to also command with hydraulic piloting, but is not the today's example. Maybe we can prepare something for the next time. And okay, the cycle we want to simulate is this one. We start with normally closed distributor, and all the power that is generated by the pump is discharged through the relief valve. After 1 second, we activate the system, switching the distributor and connecting the pressure line to the head side of the cylinder, commanding the cylinder in exiting. After 2 more seconds, we activate the regenerative valve, and we will see the speed up of the cylinder during the exiting. 1 more second to conclude the exiting of the cylinder, and then we switch again the distributor to connect the pressure line to the rod side, controlling the retraction of the cylinder. We have a total time of 6 seconds for the cycle. We will simulate 11 seconds to have a general overview of what is happening in the system. Okay, to have a complete overview of what we expect to have, we have a phase 1 where the pressure is discharged through the relief valve. Phase 2, where the distributor allows us to push the oil in the head side of the cylinder, commanding in exiting. During this phase, the discharge oil or fluid, whatever, passes through the speed valve and has a free way to the tank. Activating the speed valve, we have the closing of this line, and we command the returning oil to communicate with the power line through a check valve. And this allows us to multiply the flow rate that reach the head side of the cylinder, even if we have a limit in the pump generation. In the last phase, we finish the exiting and we switch again the distributor to have the retraction. So the power line goes through a check valve in the rod side, and we have a free way in the discharge line from the head side of the cylinder to the tank. The data that we have for this simulation is about general data, but also specific data. So we can starting from the power unit. We know the rotational speed of the engine, the electrical engine, that is 1000 RPM, and 10 cubic centimeter of fixed displacement pump. A tank that is open to atmospheric pressure. About the valving, the relief valve, we know the preload that we want 300 bar, and we know that we are using a valve from VIS Hydraulic catalog. In this way, I'm also able to show you how to use the data, the graph from datasheet, and how to insert this information in the model, in the virtual model. And the same is for the 2 check valves that we have in the regenerative line, and the speed valve, the regenerative valve we have close to the cylinder. More, we have generic information about the distributor. We know that the loss of pressure is about 5 bar at 30 liters per minute in the power connection, so in the connection P to A and P to B. And also it loses 2 bar still at 30 liters per minute in the returning line. Plus, we have the pipe connection to the actuator. We have a 30 millimeter of internal diameter piping that has a length of 1 meter. The cylinder, standard information for the cylinder about the piston diameter, 50 millimeters, the rod diameter, 20 millimeters, and the total stroke, 600 millimeters. A very important information now is the last one, that is the type of oil we want to simulate. That is an ISO VG 46 at 30 degrees. So we are simulating a cold oil. And it is possible to insert the type of oil we want to simulate, and it is possible to run different simulations. So changing temperature, the ISO VG oil we are using, but also specifying personal parameters like different density, viscosity, bulk modulus, but also the percentage of air we have inside the fluid. That normally we use a standard value of 0.1% of volumetric percentage of air in the fluid. That is a mix of air and industrial oil. Okay, we have different steps in this example. The first one will be the modeling of the circuit, so building the layout of the model. And plus, we will insert the parameters for each component. Then we can start a simulation. We can check the functionality of the model with an animation of the scheme. And last one, the most important, is we can plot the results, the values in time of every variable that we have in the schema, in the model, like pressure, flow rates, positions, and also loss of pressures, leakages, and so on. I will move to OpenModelica. Okay, I switch here. I will keep the circuit on the right to allow you to orientate in the model. This is how OpenModelica shows the first page. This is here on the top left our library that is divided in categories. I can open first, create a new file that I will call web1. This is the diagram that shows, and you will build graphically the circuit. And I will immediately extend the sketch area, since so I can work without limitations. Okay, there is also a page with the code. Everything we do graphically is converted in code, but as said, we don't need to look at the code side, at least for today. So I will remain in the diagram view. I can start to build the diagram looking for the pumps. So it is in sources folder. I'm looking for the fixed displacement pump here. We have different pins. The blue line is the propagation of the hydraulic circuit. There is also a yellow one that suggests us to complete the kinematic, the mechanical side that we have on the shaft. So I need to go in the mechanical library in the rotational folder and bringing the motor that is just a simple source of rotational velocity. And I will connect a source, a constant source to communicate how much is this rotational speed, that is 1000 RPM. Now I will complete the hydraulic side starting from the tank. Before the tank, I need the connection. I use a node to divide, to have different connection in this case, and then still in source I will use the tank. In source because the tank is a source of pressure. It is very important in our library to identify the characteristic of the element, since we have just one very important rule for the build of the diagram with our library, that is to distinguish resistive or generative elements and compare these to the capacity elements. So I mean, we have the capacity elements that are chambers or all source of pressure, and we distinguish them to all loss of pressure or generation, loss of pressure or generation of power in the library. So we always alternate the elements that have the blue pin with the elements that have red pins. The only exception is for the node that is just a propagation of a characteristic of the capacity element, that is in this case the tank. So the node always have one blue pin and all the other and others red pins. Here I have the pump, the volume that represent the amount of oil we have between the pump and the distributor. Now I can look for the distributor inside the distributor folder here, and connecting the source and the return line directly. Okay, now I have the piping to insert the piping, in this case using two pipe that represent the capacity inside the pipe. Here on the left, since I already used the capacity, I need to split the connection using another node. Okay, with a mirror to create the connection. I can conclude with the speed valve to the side that is still in distribution to valve, and taking this one that has an open center. I need, before to use the cylinder, I need another volume. I will use a volume with 3 pins here to connect on this side, and then I conclude with the actuator that is under actuators, cylinders, double cylinders. Here I can, not this one, that is a double rod. Okay, I can mirror and connect, still respecting the rule about each red pin with the blue pin, and the same for the returning line. In this case is the headline. I can complete with the check valves this side. that is here, rotating. All the valving here are also the check valve are generic element. So there is some characteristic indication about the size, but they have no response, at least not in detail. So we have indication about the setting pressure, about the size, about the regulation, and so on. And then we can characterize them with the other library, the component library. Okay, I just doubled the check valves here. The node I insert here, I use here is still, I mirror it with to point the blue pin to the volume here. Okay, it's not very compact, but the circuit should be complete. The hydraulic circuit is complete. I'm just missing three important things. That is the control of, I can close this part, the control of the valving, the electrical control, using a source, a signal that is variable in time, one here and one in the distributor, in the control unit. Okay, and second, to complete the kinematic in the cylinder. Now it is a square, and we need the translation of the linear components. And I'm using a mass. This is very, very important, since it is the mass that receive the forces that are generated in the cylinder, and elaborate acceleration, velocity, and position of the kinematic of the cylinder, of the piston. To the other side, the other shaft is empty. We simulate a cylinder without load. If we have time, I can maybe show even how can we apply load with a sort of feedback or ramp or a specific cycle load. But for now, it is empty, unloaded. And last one, the model that allow us to choose the oil we want to simulate. This is the window that allow us to personalize the oil. I will keep the ISO VG46, but I change the temperature to 30 degrees, and this will affect the viscosity. Also the cavitation, but we are not looking to the cavitation today. But in this case, changes just the viscosity of the oil and some in minor effect on the density and so on. Okay, I set up the temperature. I set up just the speed of the motor. Now I move to specify the parameters of each component. The pump is 10 cubic centimeters. Now the volume, it is, I will insert an estimation of 1 liter. That is the oil in the manifold or in the piping you have between the pump and the control unit. About the relief valve, I move to the presentation because we need, okay, the data sheet from the catalog. I will share with you. It is this valve. I'm moving to the graph here, selecting the right spring, since we know that we have a spring G at regulation with a setting pressure of 300 bar. We need one more information, that is the regulation. Okay, we could also insert the saturation, but we have no information about the saturation of this valve, so we will just insert the regulation. We see that with an increase of pressure that we have to calculate, we have here 15 liters per minute. So with the calculator, we are able to calculate the gradient 15 liter per minute divided by the increase of pressure, that is 300 minus the first opening that was 260. That was a total pressure of 40 bar. We have a gradient of 0.4 of liter per minute for every bar of increase of pressure increase. So going back to the system, I can opening the relief valve here. I set up the setting pressure, the cracking pressure at 300, and the gradient to 0.4 liter per minute per bar. And that's all for this element. The distributor general information, we have the metering for every connection. About the power line, we know that for 30 liter per minute, it loses 5 bar for PA, and for PB, 30 and 5. We have a lot of more information that we will not use right now. In the discharge line, still 30 liter per minute, we loses 2 bar, and the same for B to T. Okay, that's it for now. The piping, 30 millimeters in diameter, 1000 millimeters in length, that's enough. And we move to the speed element. The regenerative valve, that is this one. Now this is the valve, just moving to the graph. This is a parabolic curve, so when the valve is full open. So this is information for us to know, that allow us to understand the size of the valve. So this is the saturation information. We use one curve to one point of this curve. We just need, for example, now I take the more external point we have, 18 liter per minute, refer to 5 bar, and I will insert these two information in the model. Here. In the metering line, it's 18 liter per minute at 5 bar. This is okay. That is a characteristic curve that represents the size of the element. In the volume between the valving and the cylinder, I can use like 300 cubic centimeters. And in the cylinder, we know that we have, if I remember well, 50 in the piston diameter, with 20 in the rod diameter, and 600 millimeters of stroke. Also, this information I will insert also in the mass. I will say the mass has an ideal hand slope, and the coordinates, a limit of coordinate that goes from 0 to 600 millimeters. I will insert an estimation of the mass, like, I don't know, 500 kilos, with also, to make it more realistic, viscous coefficient that like 10 Newton for every millimeter per second. Okay, that is yes, viscous friction coefficient. Then it remains the check valve. So moving to the check valve, to the data sheet. In this example, I have the information, it is linear, so I will read this data like a regulation, but it's still spring G, another one, setting pressure 3 bar, and we reach 75 liter per minute at a difference of pressure that is around 7 bars. So it is a gradient of almost 11 liter per minute per bar. I will insert these two. Okay, the cracking pressure is already at 3 bar. I just insert the gradient here and here. If I had the parabolic curve, I could, for example, activate the saturation and the characteristic curve and insert this data here, but it's not in this case. What I'm still missing is, I think, just the commands of the valving. Here, I need to command the right side. I need to activate the right side of the distributor, so the solenoid needs to act in pulling. So I will stay to 0 for 1 second, and then I move to -1, that is a pull signal in 0.1 second, and remain at -1 for 2.9 seconds. Okay, then I switch. After I will activate the other side, so it is pushing. I will send a signal 1 in 0.1 second. That is the transition time of this element of the distributor, and remain 1 for all the rest of the simulation. Okay. The element remain unactivated for 3 seconds, and then we will activate. So command 1 in a response time of 0.1, it will remain 1 for all the rest of the simulation. Should be everything. I can check. We can run one simulation, setting up the parameters of the simulation. The simulated time, 11 seconds. I will increase the numbers of interval to see, to have a more detailed graphs, and I leave a low tolerance to have a very quick simulation. I can run now the simulation. I will, okay, save the model. Now the software will compile the environment that we just create, and then we will able to simulate. And okay, it finished. This is the time of simulation, that in this case is very quick. We can have an initial check of the system. We can run the simulation. We will see the cylinder exiting, and then I hope, yes, then it starts to, okay, speed up with the regenerative valve opening, closing, better closing, and then the retraction of the cylinder. I will repeat it since it is very fast. Maybe I can slow down a bit. Okay, here we can check both the pressure in the system. We can check the direction of the flow rate, if one valve opens or closes, and yes, the moving, okay, the pump. This is the main generic information to have a first overview of the system. I think it behave as we expect. We can move now to have some graph to plot the variables. We can check, for example, the pressure at the pump side. The pump side, okay, like this one, but also the pressure in the cylinder, for example. And I can also expand to have here. We can appreciate in this case, for example, the increase of pressure we have during regeneration. We can appreciate some peaks of pressure we have because of the dynamics or because of the mass of the viscosity. We have some peaks of pressure, but also peaks of flow rate. when we open the distribution to that is holding 300 bar, we open to the head of the cylinder that is empty. We can plot, for example, the flow rates, looking to the fixed displacement pump, Q-flow. Okay, this is a line that is 10 liters per minute, but it is interesting to look at the flow rate that the cylinder receives in this, and here we can appreciate the almost 60 liters per minute that we are having at the head side, while the rod side, of course, is discharging, but it's not really discharging anyway. It is giving for almost 50 liters per minute. And last one, for example, we can plot the position, the moving of the cylinder with our command, with the command we gave. So here we have the first exiting and then the acceleration with the regeneration effect. We are running out of time, so very quickly I will, in diagram view, I will remove the check valve to use one detailed model, for example, that can be designed internally or can be given by VIS Hydraulics, since they are developing with our library. And what for example, why the scope can be to analyze how the system interfaces with the valving and how they behave inside the system. Here, the icon is the same, but I can open this element, and here we can see that it's developed with the component library. And here we have the mass of the spring, the mass of the poppet, the spring, the leakages, and so on. So, and all this information can be open information, but can be also hidden information. Here I just use the spring, the right spring we have in this example, that is the G spring, not the B, the G. And we can run another simulation and see the effect that having this detailed model can bring in our circuit. It will not really change in this case, but since it is a very simple example. But okay, we can appreciate more. For example, I can plot what happens at the valving side. For example, here I can plot the loss of pressure or the difference of pressure that is applied at the valve. Here we have a very big loss of pressure, but because it is holding the pressure, because it is the check valve. It is possible to check the flow forces. Here we have, for example, some small chattering and the position of the poppet. And the position of the poppet here, this is properly the movement that poppet makes inside. Also, for example, the chattering, yes, probably it is because the rapid switch that we have in the command, since we were still exiting and then we command in the retraction, so we have the balancing of the pressures, and we know that this is quite normal to have some vibration during this rapid movement in the system. Last thing, what it is possible to do, I don't know, it is possible to change like the spring and to appreciate the effect that we have in the system. It is better, it behaves better, we have better performances, worse performances. It is possible to run a very quick simulation and see right now, for example, that we are able here we just reduced the pump pressure during the speed mode. And it is possible to simulate different behaviors and so on. I don't know if, okay, we are running out of time. If you have any question, I can maybe answer to some question quickly before to end the meeting, and thank you for your interest and participation today.
Thank you, Marco, for the demonstration. And anyone who attend to this online event will receive the slides, recording, and the deep dive page shortly. And so, if you have a question, feel free to leave them in the chat or contact us for more complex cases. And I ask you to complete our end of session questionnaire, because in addition to giving us some valuable feedback to improve our webinars and some ideas about how we can best support companies in integrating simulation into their processes, it will allow you to receive what we built in this live session, the SmartFluidPower trial library, and obtain a technical consultation tailored to your case. Of course, if anyone who couldn't attend live and is watching the recording later can also complete the questionnaire and will send by email and receive all the materials. So,
I
okay.
think there is no question, so I think we can conclude.
Okay.
Thank you all for the participation again.
Yeah. And in our next session on April 22, we'll show the significant contribution SmartFluidPower has brought to this engineering team by modeling part of our product catalog. Thank you, Jens. Thank you for the answer. And okay, we can end the session. Thank you. Have a great evening, and hope to see you at the next webinar.
Bye. Bye, everyone.
Bye.